All right, so reminder that there is a quiz due in your guys' lab. I don't normally remind you guys of this, but there is a quiz due before you come to lab this week. And remember, anything that is due in lab is due before you show up to lab. So if your lab is at 1 o'clock, it's due Thursday at 1 o'clock. If your lab is Thursday at 5:30, it's due Thursday before 5:30. If it's Friday at 9, 1, or 5:30, so on and so forth. There are some of you that accidentally got logged into the 228 lab, so you are not seeing 227 information. You should come and see me today or tomorrow, preferably. I will be here a little bit this afternoon, and then on Wednesday I'll be here from about 9 to 2. And so if there's a specific time where you know you'll be on campus and come by, definitely email me so I can make sure I'm hanging out at my office. Otherwise I might be, in another office or wandering around or something. But I will help get you into 227. Or if you email me, I have already emailed a couple people that were able to do it themselves, which is fine. But I have no problem meeting with you. I want to make sure you guys all get in. I want you all to be able to turn in your assignments. I don't want you guys wandering. I don't bite. I'm not a vampire. Please come in and see me. I want you guys to be able to get in and have all your resources, okay? So also, if you have Connect questions, come and see me. All right. Remember, if you're having a problem on the AMP website, you will talk to Sherry Zayo because she does that. That's the site that has also lab news and other resources. It's about everything to do with lecture and labs where you find notes and everything else. Connect is essentially just for where you turn in your lab assignments, such as quizzes, pre-lab worksheets that are due before your labs, fills. You have 3 of those this semester. I think I mentioned quizzes. And then also, what else? It has APR, Anatomy and Physiology Revealed, where you can go in and use resources like that. You can also view your lab manual online. You can see your textbook, the e-text online. So all of those type of resources are within Connect. So any questions, you can't find something, you're not sure what's going on, I'm the person to see for the Connect stuff, but your lab instructors should be able to help troubleshoot things. Now, there may have been a lab or two that maybe didn't get reminded that they have a quiz. So if you have no clue what I'm talking about a quiz, and you're like, that was so-and-so's lab because we didn't hear about that, then after class, come and talk to me. Or come see me by tomorrow because it is due before your lab this week, and I want you to be able to turn it in. It's worth 5 points, okay? Let's see what else. We left off talking about homeostatic imbalances and positive and negative feedback. Yippee! We started talking about the language of anatomy. So that was directional terms, regional terms, planes, and sections. Another thing that I wanted to mention to you. So if you guys read through lab news of week 1 and 2, because this is week 2 coming up, so go back and read 1 and also read 2. As you go through that information, it tells you that there was a typo in the lab manual before you guys go into lab. So it tells you what the correction is. There is a second typo also. So when we were talking about the planes and sections, your notes here in front of you, as well as your lecture textbook, is correct. So when you guys look in your lab manual and something doesn't make sense, I want you to look for it. I'm not going to tell you which ones are wrong. I want you to look for it. And I want you to see if you can try to figure it out. And then dazzle your lab instructors and be like, there's a mistake in here, I found it. All right, so look in that section, what I have pulled up now. I added a couple of notes because as you guys realize, I'm still not 100% yet with my voice. And so I rewrote a couple things because I probably had slightly messy handwriting last week. I apologize. I just added a coronal section. Another name for that was frontal, so I just wrote it on the side. Transverse section, another name for that is cross section, and a shorthand for that is XS. You may see that in your histology atlas where it says LS for longitudinal section and XS for cross section. That's what they're talking about. It's a different view. Longitudinal, I said, was like if I slice the cucumber long ways. Cross section would be like slicing the cucumber in half or snapping it in half. Then you're seeing a cross section, okay? And then the last one was median. Take the time to review where these slices are going because they've shown you a couple different ways. They've shown you like an MRI picture. They're showing you like as if they took the skull, and they're also showing you as if they sliced it on the body itself. So utilize that, because one of those pictures will make more sense to you than another, and that's all you have to remember when you're trying to remember which way the slices are going. Let's see. We also talked about body cavities. So they didn't have it written on the, let's see. They didn't have it listed. They just said posterior aspect. So I added in the word dorsal cavity, and I put a little, you guys know, this is just quick review from last time, is the cranial and vertebral canals. Okay, so the cranial cavity and the vertebral cavity is part of the dorsal cavity. Dorsal fin, right? So this is telling you it's on the more posterior aspect of the body. We said that last time. And I mentioned that it's lined by meninges. What I didn't mention maybe as clearly was that meninges are very tough, and it's different than the ventral cavity membrane lining. So we had two main cavities that we talked about, the dorsal cavity, which had two subsections, and the ventral cavity that had a couple subsections. The ventral cavity has other membrane or lining that is thinner versus the dorsal cavity. Why do you think we need something so tough like these meninges for our dorsal cavity? What are we protecting there? Protecting the brain and the spinal cord, right? So our spine, our skull and our spine, the spinal column, is like a bony armor. But then these meninges are like a softer type of chainmail underneath that. So it's another type of armor to protect, because you guys, your central nervous system, your brain and your spinal cord, if that's gone, it doesn't matter if the rest of your body is surviving at that point, you're gone. So we protect that at all costs. We will shut down other things in our body to make sure that that area is surviving. The brain gets food first. You'll learn more about that in 228. Okay, it doesn't care about the rest of you. You could have, frostbite and have fingertips fall off. You don't care about that. You care about the core of the body. You care about your main central processing unit, your computer. Otherwise, it doesn't matter if your limbs are alive and your blood flow to your fingertips, right? We don't care about the fingertips. I mean, we do, but we don't when it comes to major trauma, right? So we need this armor. So the meninges are very tough. All right, so I wanted to mention that. We already said cranial encloses the brain, vertebral cavity, another name for that was spinal cavity, encloses the spinal cord. Then we went on to talk about the ventral cavity, which is more anterior, because we said anterior, so the ventral side of the body is the tummy side, right? So that makes sense. So I circled over here, ventral cavity had the thoracic cavity and the abdominal pelvic cavity. What divided those two cavities? The diaphragm. So it had a physical structure dividing those two cavities, okay? And then we talked about in the abdominal pelvic cavity, which was below the diaphragm, it was subdivided into two areas. We had the abdominal cavity and the pelvic cavity. Does that have a structure that divides those two cavities? No. It's more like an imaginary delineating line. And we use the term pelvic brim, which is made up of a couple of structures that tell you that we're dividing this area from this area, but it doesn't have a physical barrier in between. There's no lining between separating those two cavities. Okay, so that's important to know. Another thing I wanted to mention in the thoracic cavity, which was above the diaphragm, you had the pleural cavity and the pericardial cavity, right? Pleural cavity, you have two, one for each lung. Okay, and what does pericardial mean? That was for the heart. Okay, and then I said there's this little area just above the heart. You guys remember the name? Mediastinum. Okay, so the mediastinum is not a true cavity. It's a space, but it's not lined by serosa, which is a type of membrane that we're about to talk about in a second. So, for example, this might be where a doctor may go in for a biopsy of lymph nodes to see if it's spread to the thoracic cavity. So there's no organ in that spot. It's a space, but it's not a true cavity. So I just wanted to point that out. I don't know how clear I was when I was, not feeling so great. Let's see. Also, talked about not a true barrier, separated by an imaginary line. What are some of the organs that you might find in the abdominal cavity? So we said stomach, we said intestines, and then don't forget we have other ones like liver, pancreas, kidneys, things like that, right? In the pelvic cavity, we said the bladder and reproductive. So if you were a female, you'd find a uterus. You shouldn't find one if you're a guy. There are hermaphrodites. Things happen. But if you're a male, you should find things like seminal vesicles or prostate. Those would be their reproductive parts for a male, right? Another thing is the end of the large intestine is called the rectum, okay? And so that is also found in the pelvic cavity, okay? So I wanted to point that out. And then now what we're going to do is we're going to finish up with the ventral cavity membranes and the abdominal pelvic regions and quadrants. So finish up chapter 1. Then we're going to move on to chapter 2, which is, yay, chemistry. And so I just wanted to kind of review that a little bit, throw some stuff out there real quick for you guys. Let's see. So if we go to ventral cavity membranes, it's found lining the inner walls of the ventral cavity and outer surfaces of the internal organs or viscera. So basically, what we're talking about here is you have a serous membrane or serosa. It not only lines the cavity, but it's also suspended in the cavity, and it's a double layer, okay? So I wrote down there under A, serous membrane or serosa is a continuous layer of cells lining the ventral cavities only, because we said this had serosa or lining. And what did we say the dorsal cavity has? Meninges. That's a different kind of special lining. So that's why it says ventral cavity only. And what do we have? We only have a dorsal cavity and we have the ventral cavity. They have subdivisions, but I want to make that clear that you've got that sectioned off there, okay? And it forms 2 layers, which is continuous onto the surface of the organs of that cavity. So you end up with this double layer. One of them is the parietal serosa and one is called the visceral serosa. But I want you guys to understand, this is all serosa. It's the same thing. So they're showing you a picture here of a fist going into a balloon. So let's say I have a balloon in my hand and I take that whole outer, the actual balloon latex itself is the serosa, okay? If I take my fist and I push it into that serosa or balloon, can you see in that picture how it is now a double layer? The one against my hand, which if my hand were the heart, okay, would be the visceral side because viscera means organ. The one that's not against my heart or the hand, that's lining the cavity, the pericardial cavity, would be the parietal side of the lining. But can you see it was the same cells? It just kind of did a double loop there, okay? So that's why I wanted to bring that up. So the reason why it happens is embryologically, when you were formed, you were a hollow tube, and then things grew from the walls and filled up that hollow tube, or the ventral cavities, because they came from the wall. The membranes and the linings, which are on the wall, was then over the organs that dropped into the cavity. So that's how it ended up getting that double loop or double membrane. So again, it's the same serosa. We're just giving it a name, whether it's against the organ side or whether it's not. Now, in between that serosa, the serosal membrane makes serous fluid. Okay, the serous fluid is in between that double layer of serosa. Why do we need to have fluid in there? So the fluid's not against the organ, it's between the double layer. Think of this serosa like saran wrap. Okay, if you stick 2 pieces of saran wrap together, what happens? It sticks together. And for us, we'd call that an adhesion, like scar tissue. Okay, your organs need to move, right? Your heart's beating, it's moving. Your lungs are inflating and deflating, it's moving. So if you had this saran wrap sticking to it and not allowing for movement, it would cause a lot of friction, and in the end, that would cause a lot of pain. So we need some sort of fluid in between our saran wrap, essentially, to allow things to glide and move a little bit. Too much fluid would not be good. That would be pathological. Too little fluid wouldn't be good because you'd start to form the adhesions and stuff. So you need just the right amount of serous fluid in between that saran wrap or the serosal membrane so that it can decrease the friction. So reviewing some of that again, parietal is the layer lining the inner walls of the cavity. Parietal, think outside more. Visceral is the layer covering the outer surface of the organ. So think viscera means organ. It's against the organ side. And then the serous fluid is found in that potential space between the two layers. So if you look back at that fist in the balloon, it's not against the fist. It's between the visceral lining around the fist and the parietal lining, which is against the outside of the cavity. That's where the fluid is, in between. So, which was really the inner side of the balloon, I guess you could say, right? But your fist, your heart isn't inside the balloon, it's in this membrane. I know it sounds weird. Think about it. Play with the balloon at home. It'll make more sense if you do that. I promise. Okay. Go away. All right. So the serous fluid is produced by the serosa, or the serous membrane. It's clear and watery, and the function, again, is to decrease friction caused by movement of organs within the cavity, so it decreases friction between the two serosal surfaces. So I wrote it out word for word there because I know this can be a little bit confusing on that part. All right. Let's see, what else? All right. What else do I want to tell you? Dun, 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 dun. All right, moving on. Oh, so for an example, let's look at visceral pericardium. So the term visceral tells you, what are we covering here? We're covering, and pericardium is the heart, so it's covering the organ. So visceral pericardium would be on heart surface, right? On heart surface. And if we say the term parietal pleura, what do you think we're lining? We're lining the lung cavity, not against the lung side, but the cavity side. Okay, so lines lung cavity. Okay. If I said it was lining the pericardial cavity, what word would I change for number one?
Parietal.
I would say parietal pericardium. So play with the terminology. Review this again, later today or tomorrow after you've slept on it. Go back and look at the terms, just like I mentioned with homeostatic imbalance. It'll lock it in. It'll make more sense. Quiz each other on this, that kind of thing. All right, if we look at abdominal pelvic regions in quadrants, quadrants basically are more general, and they'll use the umbilicus as the center point. And sometimes in medical terminology, you'll hear people say some really strange words that are still considered correct. So for example, when I was in a biology class in college a while back, my teacher was from England, and she was going on and on about capillaries and skeletal. And I'm like, what the heck is a capillary? And what the heck is a skeletal? I don't get it. Skeletal and capillary. Okay, so depending on where somebody is from, the word might be pronounced slightly different, and it would still be correct. But you can kind of tell where the person was educated sometimes by what terms they're using. So you may hear some people say the word umbilicus, which I think is the funniest sounding thing in the world. I say umbilicus. You'll probably make your teacher laugh in lab if you call it umbilicus. But that's the center point. So the picture on the right is talking about quadrants. And so this is a very general term, fast and easy, something that somebody might use like when they're quickly triaging a patient, or the area that somebody's having some pain. Right upper quadrant, left upper quadrant, right lower quadrant, left lower quadrant. That's it. 4 quadrants, very general. When we talk about regions, you're talking more like anatomists or surgeons. They're being more specific. Okay, so for example, here you have the umbilical region. That makes sense. It's right in the center there, right, where the umbilicus or umbilicus is, right? The term epigastric and hypogastric. Epi means upon. Gastric, stomach area. So they're saying above the stomach area. Hypogastric, hypo usually means below or underneath. So that's the term hypo. So that's pretty easy to figure out those two terms. Lumbar off to the side. Okay, so you have right and left lumbar region. Kind of makes sense, lumbar region of the body. Iliac or inguinal makes sense. You might hear either term as iliac or inguinal. Makes sense where that is, near the groin. The one that may not make so much sense to you is right and left hypochondriac region. It's not hypochondriac, which is a discussion about a type of person. This is hypo, which typically means what did I just tell you? Below or underneath. Chondros means cartilage. So it's talking about under or below the ribs. That's why you have right and left hypochondriac region, okay? So again, some of this is just straight memorization, reviewing it, saying it, look at it, see if you can do it without your notes. Then you know it. All right, so that was that. We're moving on to chapter 2. Dun, 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 dun. Okay. Chapter 2. All right, time for chemistry. And it says at the top, chapter 2 and 3, beginner's chemistry. And your book is giving you information for a 200 and 300 level A&P course. So they're going into a little more detail than we may need to do for anatomy and physiology. Because yes, we are not a chemistry course. However, pretty much every single science class you guys have from here on out is going to do a little chemistry. And as you start to get it under your belt and hear it in one class or another, it'll start to make more and more sense. And by the time you get into chemistry, you'll be like, all right, I get this. So we're only going to touch a little bit on chapter 3. The majority of chapter 3 will be covered in 228 because that's when we talk about metabolism and digestion, and that's when we get more into the organ systems is 228. So we're just going to do a little bit of chapter 3. This is mostly chapter 2. Don't go through the book, the textbook. And you are like, why? Why would a professor tell you not to read your book? One, your book's going to go into more detail than we need to do for what we need to cover for anatomy and physiology, okay? 2, you're going to think I'm lying to you. And Sherry likes to tell everybody I'm lying to you, right? So basically, when I explain things, I'm trying to tell you more like a story or to get a point across, to get a concept across to you. And for example, when you are a little tiny itty-bitty toddler kid and you're asking mommy where the baby came from, what kind of explanation does your mom give you? Probably a somewhat shortened version. Maybe the stork brought you, maybe you're born in a cabbage patch, I don't know. All of a sudden you appear, but do they go into all the details of how they made you? Probably not. And would you understand it at that point? Not likely unless you're super genius smart. I don't know. I'm not saying you're not. And then as you get a little older, you have more questions. But again, now maybe you're 5 or 6 and you're starting to ask questions and what are certain body parts. But do you really understand what all those body parts are and what kind of explanation does your parent give you? Not too crazy in depth and detail, right? And then maybe you get a sex education class in school or your parents tell you about the birds and the bees. And yet again, they may not be giving you every single detail. Okay, A&P, we cover a lot of information. It's like the tip of the iceberg. You're going to learn about this more in 228 when we hit reproductive. But even then, we don't cover every single little detail. If you went on to medical school, you'll get even more of the full picture. And by the way, we don't know everything. They still do research. We're still trying to figure things out. Everything's not set in stone. There's a lot of stuff we know about anatomy and physiology, but it's not like, been there, done that, we've discovered everything, we know everything about the body. No, because we could cure cancer if we knew that then, right? So what I'm trying to tell you is I may give you some very simplified explanations on some of these chemistry and physics terms. When you get into chemistry, you're going to be like, well, that wasn't entirely accurate. And I'll say, I know, but now you've got a good basis. And when you learn the details for what you need to know when you get into a more detailed class, you got a basis and you'll be good to go from there. Okay, so don't go in searching for all these answers in your textbook. If you really feel like you need to brush up on something, that's fine, but you just need to know what I'm giving you in the notes. So don't get crazy, all right? And what else do I want to tell you? And again, you're going to see all this in your science classes. So first we have to learn some definitions about matter and energy and the different types of energy. Then we're going to delve into atoms, elements, and bonding. We're really getting into chemistry there. And you will want to review the concepts before the next class because this info is like the building blocks or the foundation, okay? And it will help you with the later concepts because we're going to touch on these concepts throughout the rest of the semester. When we talk about hydrogen bonding, it's not just having to do with how polar molecules are attracted to each other. It has to do with how your DNA is also part of it being held together by hydrogen bonding. And then you're going to see this again when you go into micro and chemistry and some of these other classes. That's why I say, get a good handle on this. It will really make a difference, and then you won't feel lost in the middle of the semester when I'm saying, remember those covalent bonds? You're like, don't say those words. It's kind of like if you're trying to learn a new language and you don't use it, you're not practicing the vocabulary, then you can't converse, right? So, jumping and diving right in, basic chemistry concepts, definition, matter is anything that occupies space and has mass. So in general, we're just going to say it's stuff, right? Occupies space. This has matter, right? This has matter. Some has less matter than others. Okay, so mass is the amount of material in an object, and the important key here is with mass, it's always constant. And we're used to talking about stuff as something weighing something. Like I weigh 150 pounds, and you're like, okay, that's weight, but it's not the same thing as mass. So what I mean by that is mass doesn't vary no matter where in the world you measure it, okay? Versus weight would change. So you weigh different in space, you would weigh different underwater, you would weigh different at the top of a mountain, okay, when you're comparing those three areas. But mass wouldn't change in those different environments. That's the difference. So a lot of times we're talking more about mass because then we know it's a constant variable. It's not changing on us. All right, so energy is the capacity to do work or put matter into motion. This does not take up space. It does not have mass, okay? But remember, matter has mass and takes up space. So energy and mass are a little different. If we look at classes of energy, we have two major types that we're going to talk about, which is potential energy and kinetic energy. So potential energy is stored energy or energy of position, and I put the example of a battery there. The battery has energy stored in it, right? You put it in a flashlight, you can turn a flashlight on. You put it in a remote control for something, now it works, right? But it doesn't do anything, it's just sitting there. It's stored energy that you could harness and use later. Kinetic energy is energy of motion. So that's why I wrote matter is moving, okay? So if you want to think of it as like a hill, and you have a boulder at the top of the hill, if the boulder is not moving, what is it? It's got potential energy in it. It's just sitting there waiting to do something, but it's not doing anything yet. It's not moving, so it has stored energy. If somebody was able to nudge it just a little bit, or the wind blows it over, and now the boulder is traveling down, it is now expending energy in the form of kinetic. So it can go from potential energy and become kinetic energy once it starts moving. When the boulder hits the bottom of the hill, it now is potential energy if it's not moving again. It has some potential energy, not much if it can't go anywhere, right? Unless there's another hill for it to travel down again, like, you know, like Slinky going down the steps. But it's not that it has none or totally zero. I mean, there's probably like 0.000000091. I don't know. So potential energy not moving, kinetic energy it's moving. This is also going to make more sense for us when we're talking about chemical bonds in a little bit, okay? So forms of energy, there are four forms. We have chemical, electrical, mechanical, and radiant. Forms of energy can exist as potential or kinetic and can flip back and forth. So if we look at chemical, which for us is the main one we'll be talking about with chemistry and chemical bonds, is when it's potential energy when the bond is intact. Okay? So if you have a hydrogen bound to another hydrogen and it's hanging out and it's happy, that has stored energy in it. It's not doing anything. It's happy with what it is. It doesn't want to share or lose electrons or do anything else that we'll talk about in a minute. It's just hanging out. It's potential energy. If we break that bond, it will actually give off a lot of energy. So if we break the bond, it has now become what? Kinetic energy. Because we're breaking it, there's motion going on, which is really important when we talk about things like ATP or adenosine triphosphate. It's our major energy molecule. Okay, so that's why I put breaking the bonds means potential energy. I put pot, not pot, but pot. Potential energy is transformed into kinetic chemical energy, and an example would be like ATP. Every time you break off a phosphate, you break a bond, you're giving off a lot of energy. If we stick that phosphate back on, now you've stored up energy and you're ready to go for the next time you're going to break that bond. Okay. Electrical energy, movement of charged particles. So ions moving across a membrane, and a lot of times we will talk about this a lot later also. And usually we're talking about ions moving across a cell membrane. So this will make sense on how we generate energy by doing that later when we delve into this. So electrical is a type of what energy? Potential or kinetic? Kinetic, because we said move, right? It's movement. So kinetic. Mechanical energy, energy that directly moves matter. So for example, riding a bike, get your legs moving the pedals. So there's movement going on. So what kind of mechanical energy is this? Kinetic. Radiant or electromagnetic is energy that travels in waves. A good example of this would be light waves, right? Again with the sci-fi, right? So basically radiant, mechanical, and electrical, they're all talking about movement, travel, right? Moves. So all of those are all types of kinetic energy, right? All right. And let's see, composition of matter, atoms and elements. So elements are a unique substance, and the cool thing is that it cannot be broken down into anything smaller by ordinary chemical means. So for example, if you have a brick of gold, wouldn't we all like one of those, right? You have a brick of gold, and you shave it off or slice it up into the smallest possible pieces that you can. Each little tiny piece is still gold. Doesn't change what it is, you just took off little chunks of it, right? And if you break it down to the smallest possible piece you can, okay, which you wouldn't be able to do with just your naked eye, but if you break it down to the teeniest, tiniest pieces, the smallest piece you could possibly break it down to would be the element of gold, 1 atom of gold. Okay, that would be the tiniest piece. And it still has all the properties of what makes it gold. Okay, so atoms are the smallest building blocks of elements. And the 4 atoms that I need you guys to memorize for this class in particular is, I put the atomic symbols down for it. So it's carbon is C, hydrogen is H, O is oxygen, and N, anybody want to take a guess? Nitrogen, okay? And you have a periodic table in here. There's not one in the lab, but you have one in the lecture room, and all textbooks of science will have one somewhere, whether it's in the middle of a chapter or at the ends. So you also have that, and we'll see one in just a second as well. These 4 atoms make up 96% of your body weight. That's why these 4 atoms are super important. Okay, we wouldn't exist if we didn't have these atoms and the special properties, especially associated with water, which has to do with how some of these atoms interact with each other. You guys know what water is H2O, so 2 hydrogens and an oxygen bound together. Okay, so we can identify atoms or these elements by looking at their atomic structure. So the atomic structure, okay, it says atoms are composed of even smaller particles. So these smaller particles are what make the atomic structure, and that atomic structure, or 1 atom, makes up that element, is what I'm saying. So there are variations of these particles. These subparticles that we're talking about are protons, neutrons, and electrons, okay? And they are what make up the atomic structure and determine what the element is. It has 2 areas that we're going to look at, which is the nucleus and the electron cloud or shell. So with the nucleus, it typically has 2 players or particles that we're talking about. And I usually say typically because hydrogen is an exception that we'll mention in a second. And the 2 particles that you find in the nucleus, anybody want to take a guess who might already know? Protons and neutrons are in the nucleus. The electrons, by default, are part of what make up the electron cloud or shell. So I want you guys to think, if you have these protons and neutrons in the center or core of this atom, okay, that's the little blue and yellow balls that they're showing you on the blue below picture. And an electron cloud is these electrons move randomly and they zip around. So Sherry likes to say, like, pretend like it was a balloon and you have a yellow jacket or a wasp zipping around inside of there, all over the place. It's random, it's all over the place. That's like what an electron is doing. It's zipping around and spinning all over the place, and you can't completely predict where it will be at a given second, because if you went in there and did anything to check it out and take a peek, it would change what's going on. That's physics for you, all right? So that's why I said electrons move in random manner around the nucleus. And the other thing to note is typically the number of electrons is the same as the number of protons, okay? And in a chemistry class, you guys will go into much more detail about figuring out the atomic number and protons plus neutrons and getting the mass. We're not doing that in here. Okay, we're not going to go into that kind of detail. That's why I say don't read your book, don't go into that detail. But when it's equal, if I tell you that protons are positively charged and electrons are negatively charged, and if you have an equal amount of both, what kind of charge do you think an atom would have if they're equal? Neutral. It'd be neutral. There wouldn't be a charge. So that's why I say when you have a stable atom, it's electrically neutral, because it would be the same number of protons, the same number of electrons, okay? When we talk about ions in a minute, it'll make sense that it is now not stable and it's looking for a buddy, okay? So with protons, it says positively charged particles. I usually write a plus sign, or you'll see me write P with a plus, meaning a proton. Neutrons have no charge to it, so they're neutral, and sometimes I write that as N, or an N with a not sign or a zero there, tiny zero. Electrons, you'll usually see me write as E with a minus because they are negatively charged, okay? So this is just a little bit of shorthand that you'll see sometimes in the textbook or when you get into your chemistry classes. So electrons and protons, same number, equaling out makes it electrically neutral because, again, the neutrons do not add any charge. That's why it doesn't matter on that. You can also think of the electrons and protons as being similar to like a magnet. So if the protons are in the center core of the atom, it's kind of keeping those electrons somewhat close to its core, right? It's not a strong magnet, but if you have a positive charge, it's slightly attracted to that negative charge. That's why these electrons don't just fly off and disappear and seep out of that balloon that I just talked about. They're kind of staying around that nucleus and just zipping around all over the place, okay? And so the cloud model is the first picture there where it's just talking about how, okay, move out of the way. There we go. Where that's the model that's saying you don't know where the electron is, but it's buzzing around. We can draw a model that helps us understand how well this atom wants to interact with something else. Would it like to make a bond or not? Does it want to share an electron or steal an electron? Okay? And so the electrons aren't sitting in this shell model that we have here. But this is a way for you to understand how they pair up and what it would look like. Okay, so that's not a realistic, it's more like this is the cartoon drawing so you can understand the concept. Does that make sense? Okay, so what they showed you there, come on. So what they're showing you there is in the nucleus, for example, they're saying there are 8 protons and 8 neutrons in the center core of the atom. And then they drew this first line here, which is a shell, an electron shell. And so they have 2 electrons, 2 yellow dots paired up next to each other, because electrons like to have buddies, okay? They don't do ménage à trois. They don't want to do that. It's just pairs. That's it. So the second or outermost shell gets a special name. In this case, it's the second shell, but in another atom, it might have 3 shells or 4 shells. Whatever the outermost shell is called the valence shell, okay? I'm probably jumping ahead. Am I jumping ahead? I am jumping ahead. So you'll know what I mean by a valence shell in just a second. So, but that's the outer shell. And that's what tells you whether this atom will react with something else or not. Okay? And in this case, in this valence shell, it had 1, 2, 3, 4, so 2 pairs that are paired up, and a single one and a single one, okay, on the electrons. So what I'm going to tell you in a second is it has 2 potential pairings that it could make, 2 bonds that it could make with another element or atom. So if we look down, it says identifying the element, the main factor is going to be the number of protons, okay? So what we say is when we look at the atomic structure, the number of protons is the defining factor to help identify the element. It's still important to know the number of neutrons and the number of electrons. Let's say on something you couldn't tell what the number of protons was, but you could see the number of electrons. Would you know how many protons there are? Yes, because I just told you a minute ago that if it's stable, it's going to have the same number of electrons as it does protons. So you can kind of, this is kind of like when you learn addition and subtraction. It's like the forward or backward. You could figure it out one way or another. Or multiplication and division. If you multiply something, you could divide it and get the back and forth of it, right? That's all I'm saying here. So all protons are identical. It's the number that is different that defines the element, okay? So for example, this one right here is carbon, and carbon will always have the same number of protons. That's what makes it carbon. But we're going to learn in a second that some of those other things can vary a little bit, and it's still carbon. Because if it has the right number of, how many protons do you think carbon has, if you guys can tell from your notes? So it had 1, 2 electrons in the inner shell and 4 on the outer. So how many total electrons? 6. So if it has 6 electrons, it has 6 protons, right? So I also told you needed to know nitrogen, and here's oxygen, and here is hydrogen. Hydrogen is our one odd man out. He's the only weird one that only has 1 electron. He also has, what do I want to tell you? So he has one proton, that's 1 electron, but he doesn't have a neutron. He's the weird one, okay? So the other thing to know is, aside from hydrogen, hydrogen only likes to have 1 other buddy, so he is happy when he has 2 electrons, meaning he's paired up with somebody else, because he only has 1 on his own, right? So if he can share an electron with somebody else, he will fulfill his valence shell, because that inner shell only ever gets 2. All the other shells like to have 8. Once you fill up with 8, you go on to another outer shell after that. You start filling up with 8 again, if you can, depending on how you're bonding. So what we're saying here is these last guys right here, we're not going to talk very much about these guys, because can you see helium has 2 electrons in its valence shell, which is its inner shell, which only gets 2. So he is not going to be reactive. He's not looking for a buddy. He has his buddy. If you look at neon, same thing. He's got a full 8 in his shell, and if you look at argon, he's got a full 8. If they're completely filled on their valence shell, it means they are not going to be attracted to anybody else. They don't want to bond. They want to be left alone. They are completely stable by themselves, so we call those our inert gases. Inert meaning they're not going to do anything. So we don't really talk about them too much in our class, but that's why I just wanted to point that out. Let's see, what else do I want to tell you? And our atoms like the number 8, like I said, 4 pairs total in its valence shell, except for hydrogen. He only likes 2 in his valence shell to be stable. If we look at isotopes, this is where I said things can change just a little bit. So with isotopes, it says atoms can differ in their atomic structure because the number of neutrons changes. So isotopes, it's due to neutrons. So it says structure, same number of protons and electrons, but different number of neutrons. So if you look at carbon 12, carbon 13, carbon 14, what is the same between all 3 of those types of carbons? They all have 6 protons. Because the protons are all 6, they're all carbons, period. Okay? Because it has 6 protons, it also has 6 electrons. But notice that the neutrons change. Carbon 12 has 6 neutrons, 13 has 7, and carbon 14 has 8 neutrons. And then I wrote one is more stable than the others. So the one that's more stable is the one that we see more commonly or all the time. So carbon 12 is the common one, okay? And if you look at carbon, when they talk about carbon dating, You know, like when they're trying to figure out how old the dinosaur bone was or how old the human remains are, and to decide whether it is a new human species, the humanoid of some sort species or something else, or how old a tree is, or how old this geological strata area in the rock is. They're talking about carbon dating because carbon-13 and 14 are not stable. They're not the common one. So they are deteriorating and breaking down. And based on those numbers that they will run, you guys don't have to worry about it for here, they can determine how old something is based on those calculations. That's all it's saying. So there's isotopes out there. They use isotopes in medicine. Okay, they'll radiate you with something, get it attached to maybe check like your thyroid gland to see how it's functioning. And then they can measure the half-life and see how quickly it deteriorates and see if your thyroid is functioning the proper way or not. So we use this stuff even in medicine, cancer and other things. So just putting it out there. You don't need to know it to that detail in here. Just know that why is it an isotope? It's the number of neutrons that makes it an isotope. Protons remain the same. That's why it's the same element. It's still carbon. All right, cool. See, we're flying through this stuff. Not too bad. Now we need to learn a few definitions that you'll need to know. The difference between a molecule and a compound. So a molecule is a combination of two or more atoms held together by chemical bond. Okay? And a compound is a combination of two or more different atoms. So here's your key word. All right? So if I give you guys a couple of examples, let's say you have O2 and let's say you have H2O. All right? Which one is a molecule? Is O2 a molecule? Yes, because it's two or more atoms. It's saying there are two oxygens. This is called the molecular formula. You don't really have to know that. But the molecular formula is to tell you how many molecules of each atom is there. And it's saying there's two oxygens. What about water? Is that a molecule? No? Is it a molecule? Does it have two or more?
Yeah.
It has two or more, right? It has three. It has two hydrogens and an oxygen. So it is also a molecule. I put an M there. Okay? Now, is oxygen, and O2 is, we don't find oxygen just by itself. It's always going to be paired up with another oxygen or with something else. So that's why I write O2 and not just O by itself. If I say, is O2 a compound? Is it two or more different atoms?
No.
No. So oxygen is not a compound. Okay? What about water? Is water a compound? Yes, because it has hydrogens and oxygens. It's two different atoms. Okay, so it is a compound. So something can be a molecule and a compound, and all compounds have to be a molecule, right? But not all molecules are going to be a compound. So play with this a little bit. See if that makes sense. So I'll write over here for a molecule, you had O2 and as an example. I can talk today. And compound was just H2O. So that's your main word, different. It's got to be two or more. If it were just H by itself, it's not a compound, it's not a molecule. And think about compound. Like compounding pharmacy, they're putting stuff together, right? And just think it's got to be two different things if you're going to compound it together. So it's got to be two or more atoms. And so just an H by itself would not be a molecule either. It'd be an atom, but it's not a molecule because you didn't have two or more. Okay, so review those definitions, make sure they make sense to you. Let's see what else. So anything that has a bond would make it a molecule because it's two or more, right? But if it doesn't have different atoms, it can't be a compound. What about methane gas? Methane is CH4. Okay, is it a molecule? Yeah. Is it a compound? Yeah. What if I said H2? Is it a molecule?
Yes.
Is it a compound? No. See, you guys got it. But review it again later so you lock it in, right? Okay, so ions and ionic compounds. Okay, so ions are atoms or a group of atoms. And the reason I say group of atoms, because when we talk about acids and bases, you're going to see why I mentioned that. But they are atoms or a group of atoms with a charge due to a loss or gain of electrons. So I like to think of ionic stuff, meaning that you have stolen or lost an electron. Okay? So you are not sharing if you're an ion. You have lost it or you have gained it by stealing it. Okay? All right. So if you have lost an electron, it means you will be called a cation. Okay? If you've lost an electron, does that make you more positive or more negative? Makes you more positive, because if you lose an electron, you're losing negativity, thus you're becoming more positive. Okay, so a cation is a positively charged ion then. By default, an anion, saying that you gain an electron, if you gain electrons, you are becoming more negative. So you end up with a negative charge. Okay, a couple other ways to help you study or remember the difference. You could look at the word cation and the letter T has a cross in it. That'll help you remember it's a positive, right? You could look at anion. A is like not or negative or something like that. So you could think anion, or N in the anion is N for negative. You only have to memorize one way, and then you can go with it. Yes?
The way I learned it is cation, it's a catastrophe if you lose something.
There you go.
And then an anion is another one.
See, another electron. But remember, depending on what you're using, he's got it down for him. So if you use that definition, you got to remember, what are you talking about? You're adding or subtracting an electron, and what does that make that element? That's a great example. Good job. So whatever it takes for you to memorize it, whichever way makes sense to you, use it and stick with it, because that's what works for you, right? Okay, so let's see, what else do I want to tell you? Okay, so the octet rule. I started to talk about the octet rule, and this has to do with that valence shell. I was jumping ahead. So the octet rule, I said that outer shell, other than hydrogen, likes to have 8 electrons total. That means it would be a full valence shell. If it has a full 8, it no longer wants to interact with anything. Those are our inert elements that were on the far end column of the periodic table. So octet rule means atoms except hydrogen, because hydrogen only likes what? 2 electrons total to fill his shell. All the other ones follow the octet rule, which is 8 electrons in the valence shell. Valence shell just means outermost shell or orbit, and this is involved in bonding. This has everything to do with telling you whether it's going to bond with something or not. That's what the valence shell is showing you. That's what the cartoon picture of the shell model is showing you, the valence shell, so that you understand if it's going to pair up or not. So if we look at ionic compounds, they are created by electrostatic interactions between cations and anions, which form the ionic bond. And if you have a strong positive charge and a strong negative charge, think of them like magnets. So this wouldn't be like when you play Red Rover, and you're grabbing arms and you are not going to let go. It's not quite that strong of a bond. Think of it more like a magnet. It's pretty strong on some of those really tough magnets, but you could pull it apart if you wanted to, right? Okay. Especially later you'll learn in chemistry, you can pull it apart with something else that's polar. So we'll kind of talk about it in here. So ionic bonds are strong, but you're going to learn in a second that when you share electrons, it's stronger. Okay? So an ionic bond, let's talk about these guys first. This is where I said you're either losing an electron because somebody stole it, or you gave up an electron so that you could become more stable as well. Okay, so think about this as stealing electrons. This is not sharing, not sharing, not sharing, not sharing. Okay, you don't want to share with your sibling on this one, but you're being forced to be close to them with a magnetic bond. Okay, this is like step siblings maybe. No, I'm kidding, I don't know. Whatever works for you in your story in your head. All right, so this has to be an overall positive paired with an overall negative is what we're saying. A cation with an anion, right? And also ionic compounds means it's also an ionic molecule, right? Yeah, molecule, 2 or more paired together, it's a molecule. Okay, so again, think of ionic as what? Stealing electrons, creating then an anion and a cation, which will then form the ionic bond. Okay, so for example, I know the picture is pretty tiny up there, but you can kind of see the electrons at least. So the purple one, the purple atom they're talking about there is sodium. And the main thing we want to look at is the valence shell and how many electrons are unpaired in its valence shell for sodium. It has one unpaired electron. If we were to count all of the electrons, it has 11 electrons, also 11 protons. The protons is what tells you it's for sure sodium. And we have one unpaired one. So that means, I'll come back. Okay, so for chloride is Cl for chloride, and it has a total of 17 electrons, thus also 17 protons, right? It has 17 electrons. How many are unpaired in its valence shell? It has one unpaired one, but it has 7 total electrons there. 6 of them are paired up and only one is all by his lonesome. So think about it this way. What do you think is easier? For sodium to gain 6 electrons or for chloride to steal 1 from sodium? Chloride's going to steal 1. So if it steals 1 from sodium, sodium now becomes positive or negatively charged. It lost its electron, so it's now 1 positive. 1 electron means 1 plus sign. And chloride gained an electron, so he has now become what? Negatively charged. These are now ions, right? These are a strong full charge, and I'll make sense in a minute when I talk about something that's a partial charge. So now sodium is positively charged, chloride is negatively charged, and they are super attracted to, don't use the sibling analogy then. They're super attracted to each other. And so they're going to come close, but they're not going to grab hands like Red Rover, Red Rover. They're just going to be right next to each other. It's a good strong bond, but it's not weak, but it's not the strongest one that we're going to talk about, okay? And so that's why in the last picture they're showing you that sodium and chloride, they're oftentimes written like that. You don't draw a line between them. You're showing that the positive and negative charge are what are attracted to each other. Because they are ions, you know it's an ionic bond. And it all has to do with it stole an electron or lost one. That's why. Okay? This is also a polar molecule. We'll use that term again in a second. I'll explain what polar means. All right, any questions on ionic bonds? I thought that was pretty cool. Okay. So moving on down the road. So now we're on covalent bonds and molecules. Covalent bonds are stronger than ionic bonds. Covalent bonds are all about sharing an electron or electrons. It could be more than one. Okay? So ionic bonds, stealing. Covalent bonds, sharing. Okay? So you aren't giving anything up. You're not creating an ionic charge in covalent bonds. Okay? So for example, this occurs by sharing of electron pairs. I'm going to jump down just for a second to tell you that you could have a single covalent bond, which means you're just sharing 1 electron from each atom. Okay, and so we usually denote a single covalent bond as a single line. So if I was saying H bound to an H, it would look like that, a single line. It means that H of one atom is sharing his electron with the other H, and the other H is sharing his electron with the other H. So they're sharing their electrons between. So 2 electrons are going around this electron cloud around both atoms, zipping around. Okay, that's what that means. A double covalent bond says it's sharing of 2 electrons from each atom. So up above you have the example of O, and a double covalent bond would be like an equal sign, two lines. So that means that the O on one side is sharing 2 of its unpaired electrons with the O of the other atom that is sharing 2 of its unpaired electrons. So it's a total of 4 electrons being shared around the 2 atoms at this point. Okay? If we say triple covalent bond, now they're using the example of nitrogen, and it's a triple bar, 1, 2, 3. So how many unpaired electrons did the N have, one of the N's have, in its valence shell? It had to have had 3 unpaired electrons in its valence shell. We don't care about the paired up ones. We just know that it had 3 that wasn't. The other N had 3 that wasn't. So how many total electrons are they sharing between these 2 atoms? 6. 3 from this one, 3 from this one. They're equally bouncing around the 2 N atoms. Okay? That's all that means. If we look at, if we go back up to our picture here, so H is our exception that doesn't follow our octet rule. It only needs 2. Okay, so it's showing you that I drew off to the side here 1 hydrogen atom with 1 single electron. Okay, and then if you add a second hydrogen atom, So I'm just putting H in its nucleus where the protons and neutrons would be. And he has also one single unpaired a single unpaired what? Electron. There we go. So what they're going to do is they're going to share these two electrons between themselves. Okay? If we go, and then, so H2, I told you, when you write out how many molecules of each atom you have, that's the molecular formula. This is called the structural, again, you don't need to know this for us. Structural formula is because, think of it like it's showing you the scaffolding, the structure of a building. So this is where you're seeing the lines being drawn representing your sharing of electrons, your bonds. And if you see a line, does that mean it's covalent or ionic bonding? It's covalent bonding, which means it's sharing or stealing? Sharing. If you see positive and negative full charges and no lines, it means it's a ionic bond. Are you sharing or stealing? You're stealing electrons. Okay, very good. Okay, now if we look at oxygen, I drew one next to it and I showed you which ones were paired up. So he has his inner shell, two paired electrons. We don't really care about those guys. We draw the valence shell for him, his next outer shell, and he has 2, 4, 5, 6 electrons. 2 of them are unpaired. Okay, so because you have 2 unpaired electrons, how many bonds can this oxygen make? 2. If we happen to stick another oxygen on it, which is what they were showing you in the picture here, they're showing you, and I'll draw 2 off to the side because I just wanted to show you what it typically looks like. So if you have your oxygen, you had your inner shell, here's an oxygen, his inner shell, here's his valence shell, here's his valence shell. And what I'm going to do is take the 2 already paired electrons and stick them kind of over here off to the side. Because they're already paired up, we don't care about them. They're not reactive, they're not important to us. But he had 1, 2 unpaired electrons. And we need 8, right? We want an octet here. That's why these 2 just don't pair up and say they're happy. There'd only be 6 there then. And this guy also had 2 unpaired electrons. So these 2 are going to share, these 2 are going to share, and it's kind of nice because it makes it obvious. You end up with a double covalent bond. Okay, so I'm just trying to show you like a fast and dirty, easy way to represent it. Nitrogen is the same kind of thing. Okay, so this time you had 3 unpaired, so I drew nitrogen there for you. Same thing. I'm going to draw, here's our little inner shell, right? And then we have our valence shell, pretend they're nice equal circles. And I'm going to put my paired up electron off to the side, and I'm going to spread out my 3 unpaired ones here, right? And we want 8, and look, there's another nitrogen, and he would love to share with me. So we're going to pair up this way, and look, there's your 3, your triple covalent bond, right? N, 1, 2, 3, N. Those other electrons are there. They just don't really represent them. And in chemistry, you would show them. You would have like these 2 little dots hanging off to the side showing you, hey, there's other electrons here. This is important when we're talking about polarity, but you guys don't have to go that deep into it. So what I do want you guys to do before the next class, so you can think about it, is I want you guys to practice with cyanide, not in real life, but the molecule, okay? So cyanide, I'm going to write down the molecular formula. Cyanide is HCN, and I want you guys to try to figure out its bonding pattern, like what we just did. Figure out where those covalent bonds are and how you might draw them, representing their valence shells. So you guys already know what H looks like. You already know what N looks like. C, we didn't really study, although it's super important. If you guys end up looking back up in your notes or you look at a periodic table, I will tell you now that carbon has 4 unpaired electrons in its valence shell. So that will help you figure it out. But try to draw what you think carbon looks like. And you can go back to that picture up here and see what carbon looks like there and figure out its bonding pattern. So again, play with cyanide on paper, not for real life. HCN, and go from there. Now, covalent bonds satisfy the octet rule because what we're just trying to show you there is that the outer shell of each atom should have 8 electrons, except hydrogen, which only wants to do 2. Now, we want to look at something, it's like a subdivision of covalent bonds. You have covalent bonds, but there are either non-polar covalent bonds, or polar covalent bonds. This is not the same as ionic. So this is why I wanted to differentiate. Ionic is its own thing. Full charges, right? Strong magnetic charge. Non-polar covalent bonds means that they are sharing the electrons equally. Okay? These are happy siblings. They're playing very nice with each other. They're sharing equally. This would be like oxygen or hydrogen, H2 or O2 or even N3. They're sharing, one is not stronger than the other. One doesn't have a bigger, one's not a larger atom that would pull the electrons towards it a little more. So they are sharing equally. These three are examples of non-polar covalent bonds. What it means is it's not going to be really attracted to other stuff. So later on when we talk about what water can dissolve, you're going to see water is a polar covalent bond. It will not react with something that's non-polar. It's not attracted to it. Okay? If something's non-polar, it doesn't want to bump into something. So later you're going to find out like fat molecules are overall non-polar. Does water mix with fat? So you have a bunch of butter on your hands, you're making something, bread, I don't know, whatever. You got a bunch of butter on your hands. You stick your hands under water, all it does is bead up. The water is not attracted to it. So you have to use something like soap to emulsify it and help mix it so that you could rinse off the butter or the fat. Okay, so that's what I want you guys thinking about. This is where we're going with this later on in this chapter. So a polar covalent bond, both of these are sharing electrons, but a polar covalent bond is like talking about having an older brother and a younger brother. The older brother is bigger. So who do you think gets all the toys? The bigger one, right? Unless mom or dad intervenes and says, oh, cute little baby brother, you're going to give your toys to your baby brother. But that doesn't happen when nobody's looking, right? When nobody's looking, who steals all the toys? And I don't want to say steal. Who shares but takes some more to himself, right? The bigger one. So for example, if we draw water, okay, what I did here was I drew water. The O I drew ginormous because it is a much bigger atom or element than the hydrogen atom. So I drew the H's kind of smaller. So you could think of these like Mickey Mouse ears, right? The H's are the ears. The O is the face. And so what I'm saying is I drew a bar, which means what? It's a covalent bond. But because oxygen is so much bigger, this is the big brother, he's going to pull the electrons slightly more towards him. This ends up creating a partial or slight charge. And if it's pulling more electrons towards it, is it more positive or more negative towards the O? More negative. So he's slightly pulling electrons more towards him. And the term or the thing that we end up using, you won't have to know it so much in here, but I think it's important when you see the pictures that are on here. We use the sign, it's a lowercase delta, and it would be delta negative. And that delta means partial. This is not a full ionic charge. That's what I want to make sure you guys understand. It's a partial charge. It's like a baby charge, teeny bitty, itty bitty charge. So they're sharing electrons, and if oxygen's drawing the electrons more towards it, what do you think is happening to hydrogen? It's becoming partially positive because it's slightly less electrons towards it, right? So it'd be a delta positive on this side. Okay? So all you got to think about is big brother's trying to pull more of the toys towards him. You can't have my Legos. I want all the Legos. H says we can't have all of them. You have to share some. Okay? But big brother has the majority of them, so he's more slightly negative because more electrons towards his nucleus is making him more negative, but a little bit. It's not like an ionic charge. It's not a full charge. That's why we put that little delta sign there. It's saying just a little bit more negative towards the oxygen, thus slightly positive on hydrogen. And pretty much all you have to know is hydrogen is almost always slightly positive when it's in a polar covalent bond. It can be in a non-polar covalent bond. But when hydrogen is part of a polar covalent bond, hydrogen's always slightly positive. The other atoms are always bigger. Hydrogen's teeny tiny, guys. Little itty bitty guy up there, okay? So anytime you see that, this is what sets you guys up to understand the next concept, which is hydrogen bonding. Hydrogen bonding is a very weak interaction, but it is so important. So, so important. Okay, we would not have life on planet Earth if we didn't have these hydrogen bonds. All right? This is what makes us unique, and it gives so many different properties, which is what we're going to talk about in 2 seconds. All right. So, for example, if I have a partial charge, it can now, so if we look at one of these guys here, so on the H's, I'm going to draw partial positive, partial negative. Okay, and I'm going to do that on all of these little molecules that I just put on here. And just like with an ionic charge, okay, because we have positive and negatives here, even though these are just partial, they're still attracted to each other. It's just not as strong as a bond. Okay, they're not making a line through it, so they show this by doing a dotted line, means it's a hydrogen bond, which means it's a weak interaction. So it's just between a positive and a negative, and a positive and a negative, and that's what they're showing in this picture. They're showing dotted little hydrogen bonds. It's just hard to see in a tiny picture there. Okay, so a hydrogen bond is not a covalent bond, but hydrogen bonds are able to occur because you can bond to another polar covalent molecule or an ionic molecule, because even a partial charge can be attracted to a full ionic charge. Okay, so any kind of a partial charge or full-on charge is going to be attracted to each other, which means that if I took NaCl from that earlier picture, anybody know what NaCl is? Table salt. And NaCl was an ionic bond. It was Na plus Cl minus, right? Ionically bound to each other like a big, strong magnet. If I pour water on it, what happens to the salt? It dissolves. You still have sodium ions, you still have chloride ions, but the water is now able to bond in between. So instead of having that salt crystal, it's now out. If the water evaporates, what do you think happens? Sodium and chloride can bond again. So, all right, let me zip through this last part really fast if I can. Okay, unique properties of water. So this is all about water, all the important stuff about why we have life on Earth and everything else. So unique properties of water. Water has 3 phases. It could be gas, or an example would be water vapor. It could be liquid. An example would be water is in the liquid form. And it could be solid in the form of ice, right? Cohesion is making sure I didn't miss anything on my notes. Zipping along. Okay, cohesion is the attraction between water molecules. So it's due to hydrogen bonds between water molecules, which causes them to stick together. So hydrogen bonds means there was an unequal sharing of electrons, right? Big brother, little brother caused a partial charge, which allowed us to have a hydrogen bond. Okay? And then that allowed it to be attracted to other things. It's a weak interaction, easily to break it. Okay, we can really easily break hydrogen bonds. Not so easy to break ionic bonds, definitely not so easy to break covalent bonds, but hydrogen bonds, make and break them all the time. But it is strong, but it's a weak interaction. Okay, if we look at surface tension, that is the inward pulling due to cohesion and 3 instead of 4 hydrogen bonds because of a free surface. So basically, one of those water molecules, like in this picture up here, or what I drew here, one of them is lost due to the actual surface of the water, so it kind of goes away, makes up part of the surface, making things more rigid. So have you ever done a belly flop in the water, right? It feels like you're hitting a wall. So even though you can glide through water, when you smack into it, that's a surface tension you just hit, and then you sink in, right? So it can be quite rigid and uncomfortable. Okay, some other examples would be that due to surface tension, a water spider can walk on the surface of water because he is making little hydrogen bonds to that surface, and that allows him to stay on the surface tension and not just sink in, like we would sink in, right? Also, if you think about, this is pretty strong also, if you took 2 wet surfaces, so let's say like with microscope slides, if you had water in between them and you had the 2 pieces of glass stuck together, can you just pull them apart? No, it's stuck pretty good. You'd have to slide it apart and get some break of that surface tension. Another way of surface tension, you ever fill up your water glass in the sink or in the fridge, and then you overfill it by accident, you're like, oh, and you don't want it to spill, right? And you could see that bubble of water, but it hasn't spilled over yet. That's the surface tension holding the water molecules together, preventing it from spilling over. But once you allow too much gravity or force and then it tips over, then you've broken the surface tension and it spills over. But that's another way of thinking about your surface tension. Water has a high specific heat, also known as high heat capacity. So that just means that it takes a lot of energy before it can change temperature. So for example, if you were, our bodies are made 50 to 60% water, I told you earlier, right? So 50, 60% water. If you were in an air-conditioned room and then you went outside, and let's say we're visiting Arizona and it's 100 degrees outside, it would take a little while to really warm you up, okay, because you went from being so cool, and it would take a while because of the high heat capacity of water. An easier way to understand this, so you take a pot of water, metal pot, stick it on the stove top, right? Don't do this at home. Please don't come back and tell me that you burned yourself because of me. So you put the pot on. Does the water boil instantly when you turn up the heat? No, it takes a while. Watch pot never boils, right? It takes a while. So before it gets close to getting too hot, okay, if you stuck your finger in the water, it's not boiling, please don't do this. If you stuck your finger in the water, if you've ever done that, was it really hot? We're not close to boiling yet. No, but if you touched the pan on the outside, the metal, was it really hot? You burned yourself, right? So the water, high heat capacity, took a lot of energy before it warms it up enough that it caused it to change its temperature and become really hot also. The pot, though, made out of metal, does it have a high or low heat capacity? Low, because that heated up really fast, right? And you'd burn yourself if you touch it. So if you think about the pot thing, that will help you guys understand high versus low heat capacity, metal versus water, and why water is amazing. High heat of vaporization. So this takes, again, a lot of energy to make water go into the gaseous phase or to vaporize it. Vaporize sounds like such a sci-fi term, but we do this all the time, right? So this is where water, in order for water to leave the surface tension or of your body or from liquid, okay, that's the high heat of vaporization. So we use this process in sweating, right? Why do we sweat? To cool your body down, right? You get hot, you start sweating. You could be a nervous sweater. I mean, it's a little different, but you're getting hot, you cool it down. So when water molecules leave, they actually take the heat energy with them, and that's what helps cool you off, okay? So water is also polar, and when water can dissolve other substances due to its polar properties, like when I was talking about adding it to the salt, right, NaCl, it's called a solvent, and water is actually called the universal solvent. So I wrote that in there for you. So substances that can be dissolved by water are also polar substances, okay? And water is very reactive. So reactivity, it functions in many chemical reactions. And the two reactions that we will talk more about is one is called dehydration synthesis, and the other one is hydrolysis. So if you think of the term synthesis, means you're building something. Dehydration, you're pulling water out. So basically you're taking an H and an OH from two different molecules. If you put H and OH together, you have formed a water, so you have dehydrated this new molecule, and you synthesize something, you built a bigger molecule. That's why it's dehydration synthesis. We'll talk about this more later. Hydrolysis, hydrolysis, look at the root of the word. Lysis, to break or to cleave. Hydro, water. So you're using water to break it off. What happens is you put water in, one H bonds to the end of one new molecule that you made, OH bonds to the other. So that's how that part works. And I've gone over time. So we will talk about cushioning for protection, like CSF, protecting your brain. And we'll start with acid and bases next time. And for those of you that can stay for a clicker, I'll put the clickers up in just a sec. Good job, guys.